alpha, and C2 basically tells you how much you have in beta. Right? And then you can take the complex potential transpose of that, the element, and you will get C1 star and C2 star. Okay. And so this is sort of how we're going to be describing states in this sort of system. But I guess before we go there and before we discuss this in more detail, I want to actually focus a little bit more on the characteristics of these spaces, state alpha and beta. What are their important mathematical characteristics? And what is very important is that they're orthonormal. And so what does it mean that they are orthonormal? That implies two things. It means that they're orthogonal, and also that they're normalized to be one, basically, if you sum over all of them, like here. So this is basically the characteristic for them being orthogonal, that if you take the inner product, it's one if they're the same, and they're zero if they're not the same. And then if you take the sum over all of them, I guess is this what you call outer product? Not sure. Then it always gives you identity. So I guess what I would like you to ask is to just convince yourself that these properties are true for these two states. So maybe you can just write it down, or somebody write it down on the board. Can you do it, Bertram?
I can't.
You can.
No.
Come on, Bertram.
No idea. This is my first time with all this stuff.
No, that's why you got to do it. That's why you got to do it.
That's why.
So yeah, it's really easy. So let's just see if you can do it.
All right.
So basically, what I'm asking you to do is to plug alpha and beta into this equation, right? Where basically n equals 1 if it's alpha, and m equals, well, they just count them, right? So I guess there's two cases that you kind of have to examine. One is where these are alpha alpha, and the other case would be where this is alpha and beta, and see that in one case you get 1, and the other case you get 0. Okay. Right? So can you write the vectors corresponding to this notation?
Actually, I'm actually not that familiar with that notation.
Right, okay. That's great. That's great. So, okay. So let's just make sure that you understand what this sort of means, right? So, okay. This is a bra, and this is a cat, right? So the bra, you have to write as a row vector, and the cat we have to write as a column vector. Okay, so just go ahead and do that. Write 1 0 0 1, just like that. Exactly. Okay. Now in this case, this would be alpha, and this is beta, right? So now do the multiplication and see what the result is. So exactly. So you do. Exactly. So in this case, this would be 0, right? And that makes sense because in this case, n and m are not equal, right? Because it's alpha and beta. So now you do the same thing for alpha and alpha.
Right. So 1 0, and we do the
Exactly.
This is the cat, this is the bra.
Exactly.
It's a bracket notation, so the one on the left is the bra, and the one is the cat. Together is the bracket.
Okay. Okay, great.
So the camera.
Okay, perfect. Okay, makes sense. So they're orthogonal, right?
Yeah.
And then, how do you evaluate this? Can you do that also?
All right, so now we have the column vector first.
Right, exactly.
So let's do a of alpha, so we can have 1 0. And then we have the bra, so we have 1 0 like this.
Exactly. And then you have to add because it's the sum, right?
Exactly.
So then you do the same thing for beta again. So do plus and then beta beta. Okay. And then what is the result of that?
Just
So it gives you a matrix, right?
right. Yeah. So we get 1. It's 1 plus 0 plus 1, right?
Exactly.
We get 0 plus 0 plus 0. Right? And we get 1, 0 here. We get 0 here. We get 0. So basically,
Exactly. Perfect. Exactly. Sweet.
all right. I'm
So,
convinced.
so you kind of understand sort of, I guess, these two properties.
Yeah.
And these are very, very, very important properties for these basis sets. And you kind of have to remember that if you have like a basis set, you always want them to have these properties. Sweet. Okay, then let's look at how we get something. Ooh, this does not look very good how compared to the orange part, does it? Well, I guess if one sort of tries to remember what expectation values or how they are defined in quantum mechanics, then one basically sets up the equation as such, and you can solve it. And I guess the important thing to note is that if you basically solve this equation in a general case, where you have an expectation value for some observable A, that then you have sort of these square products, right? There's C1, C2, and if you just look at the state itself, you usually only look at either C1 or C2, like how much you have of alpha or beta, whereas here it's kind of a little bit different because you always look at the product of the two. And so basically it seems like in order to evaluate an expectation value of something that we want to measure, it would make sense to have an object that describes basically these square terms. And so if we set up some object that we define as such, right, then we obtain a matrix that obtains basically all these square terms that seem to matter when we want to evaluate some expectation value of some observable. And so this basically is what we call density matrix. And it's really nice because it basically describes all the important characteristics of the spin state of what's going on, and it can be easily used in order to see what your observable is if you measure it. So, and then basically a nice way of how to calculate your expectation value is usually just to evaluate this part here in the bottom. It's the trace of the density matrix and some operator that corresponds to your observable, right? And so basically, this is a very easy mathematical operation to do usually to calculate the trace of operators like that, and this is why we like it.
Can we actually demonstrate that the expectation value and the trace of rho A are the same thing?
Right, exactly. And this is what I'm doing here, basically. So, yeah?
So, expectation value, that's a property of psi, not of A, right? Or I guess it's a
no, it depends on both, right? Because
but generally you're more interested in what psi is and A is well defined.
well, the nice thing is if you have all the information here, you're independent of your A, right? So say you have, and this is exactly, you're pointing at exactly the problem that this is solving, right? So here you have an expectation value, and this expectation value is a function of psi and A, right? So they're sort of connected to each other. But what rho does for you, the density matrix, is that it describes the state and what's going on with your spins independently of what you're going to be measuring at the end.